Welcome back for our last discussion in Chapter 7. We're going to wrap things up in applications of integration by looking at a very specific out of geometry and math kind of setting and look into physics by looking at an example of work. Now, if you've taken physics, you've maybe come across the idea of work before, but I've reminded us of it up here. Work is equal to force times distance. So a force that's applied times a distance traveled. That's the amount of work that has been done. Now, if you're in a physics class, you typically write things in very standard units. The two types of standard units we have are the metric units, which will be Newton meters. Newton is the standard unit of force. Meters, standard unit for distance. In the other system that we use here in the United States, you would use foot-pounds, feet standard unit for distance, and pounds standard unit for force. So typically we talk about work in one of two contexts, either as foot-pounds or Newton meters if you're in physics. But understand, because we're more concerned here with the calculus behind work, we're not as concerned with unit conversion. We'll leave that for the physicists. Then what we're going to end up with is sometimes you may have standard units. In other examples, we're okay giving our answers in other random units, like, Newton centimeters or inch pounds. Maybe it doesn't match up quite correctly. And so we're not as concerned with conversions as we are with the calculus or the math behind the development or the computation. And so just to give it as an example to start, a nice simple example to warm up this idea of work is, say we have a train, and a train pulls a 5 metric ton crate for 2 miles. How much work is done? Now in this case, we can really think of it quite plainly. We have 5 metric tons. If we wanted to convert this into kilograms or something like that, we could. Or maybe even if we want metric tons, we can convert to pounds. But either way, say we have a 5 metric ton crate and it's traveling a distance of 2 miles. How much work is done? Well, work is force times distance. And so we don't want to overthink this. The amount of work done here is exactly 10, 5 times 2, 5 metric tons for 2 miles, force times distance. And in this case, my units are very non-standard, right? They're not very pretty. It's metric ton miles. So 10 metric ton miles, I would say. So just to give us the idea that A, we don't necessarily always work in the standard units that a physics class would, and B, don't overthink it. It is simply force times distance. We get 10 metric ton miles. Now, of course, if this was all that work was, force times distance, and it was that simple, then why are we talking about it at the end of Chapter 7 in applications of integration? I don't see an interval here. So where does integration come up? Well, the integration comes up when we do not have constant forces. And say we are calculating work with variable forces or distances. So maybe the force changes as I move. Right? For example, what if this crate that maybe started out 5 metric tons, maybe it started losing weight as I started to pull it. Some of the weight was sliding off the back and falling off, and it was losing mass or losing weight over this 2 miles that it traveled. There was a leak or something in the bottom, and stuff was falling out. Then I would have a variable force. Why? Because as I move, the force or the weight of this object is changing. To give you a very practical, real-life example, in physics even, you talk about springs. And if you think about how a spring works at rest, there's no work required to do anything to hold it there. It's just sitting there. And as you compress that spring, it may be hard to compress it, but the more and more you try to compress that spring, the harder and harder it should be to maintain that compression. Likewise, the same for stretching. And so a spring is a nice example of a continuous varying force, a force that varies continuously as you compress or stretch it. Another type of varying force that we will look at is gravity. Gravity is another type of varying force. That as we move away from the center of the earth, we have less and less gravity acting between us. So you become, quote unquote, weightless, right? There's less gravity. You weigh less, at the top of a mountain than you do at the center of the earth. All right, so gravity, springs, these are two examples we're going to look at of varying forces. There's a lot out there, but these are just some simple examples. And again, we're more concerned with just the calculus behind these calculations, not so much work as a whole in all the different types of examples. And so work with a variable force or distance. So say we have a distance, so our x-axis represents distance, maybe from A to B. So the distance traveled is b minus a, that's how far we've gone. And say as I move, the y-axis represents force, and the force changes as I move from A to B. So as I move from distance A, or point A to point B, the force of this object's changing, right? It starts here, the force increases a little bit, starts to flatten out, and then increases again. And so the force is continuous and changing as we move along the x-axis from A to B. Well, how would he calculate the work done if it's force times distance? Well, since it's a continuous varying force, what I could do is approximate it. I could say, okay, well, let's just take a delta x size step away from A, and let's just assume the force is whatever it is at A. I measure the amount of force, how much it weighs, or whatever I'm measuring. The amount of force at point A I measure, and I just assume it's constant, the force is constant from A to this other point right here. And then at this point, I stop again, and I measure the force at this point. I assume it's constant for another small delta x distance. I've taken an equal size step, and I measure the force at that point, sorry, here. I assume it's constant over a delta x distance again. And then once I take that delta x step, I'll measure the force again. Now remember, work is force times distance. Force represents the heights of these rectangles. Distance can be represented by this delta x distance here. And so the amount of work would be then the area of that rectangle. And so what I could do is I could approximate the amount of work by then measuring the force every delta x distance, dot, 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 assuming it's constant force over that delta x distance, then the work would be the height of that rectangle times that delta x, height times base. And so the amount of work done would be approximately the sum, and say we divide it into n subintervals, and it was assumed to be constant at each one of these xi's times delta x. All right, it would be the sum of all of these works, these areas of these rectangles, these forces times these distance, right? Constant force assumed over that distance traveled, adding all that work up would approximate the work from A to B. Well, this looks exactly like a definite integral. In fact, it is, and that's why it's a very nice example of integration. Because to get the actual work done, I would need to take the limit as n goes off to infinity. And funny enough, if I take the limit as n goes off to infinity, that is by definition a definite integral now. A to B, the force function f of x dx. This is now equal to the work done from A to B. And so where does the integration come up? It comes up with variable forces, and it turns out that work is the definite integral of force over distance. It makes sense, force times distance, right? You're adding up areas of rectangles. Distance is infinitesimal, f of x, right? That's my force function. Adding all those up continuously gives me work, giving me a definite integral. So in some way, if we relate the definite integral to antiderivatives, we can relate work to knowing an antiderivative of force. So if we have a force function, we can take its antiderivative, plug in the endpoints of the distance traveled, and calculate work. And so this gives us a very nice formula to use. And so what we're going to do now is we're going to go look at those two examples. So work becomes the definite integral of force over the distance traveled. And now let's look at some very specific cases. So I wrote down two rules for us that we're going to use, Hooke's law and gravity. Now, Hooke's law tells us that the force required to stretch or compress a spring is proportional to the amount stretched or compressed. Proportional just means they differ up to a constant. So the force is related to the distance stretched or compressed multiplied by a constant. We call that the spring constant, and I'll use the letter K. So the amount of force required is dependent on how much you've stretched or compressed it. X is the amount stretched or compressed. And K is some constant. That's our proportionality constant, right? They're not equal, but they're proportional to each other. So there's some constant that relates them. We call this the spring constant. And so when we're dealing with springs, we have Hooke's law, which gives us a very specific force function to use. And remember, work is the definite integral of force over the distance, in this case, stretched or compressed. In the same way, gravity is very similar, has a nice force function as well attributed to it. Gravity, Newton's law of gravitation, says that the force of attraction between two objects, gravity, force of gravity, is inversely proportional. Now, that's not necessarily the best word to use, but we'll use it. Inversely proportional to the square of the distance between them. And so the force of attraction or gravity depends on the distance between them. So x is the distance between the objects, and it's important to understand the distances between their centers. Just to clear this up, if I were to ask you right now, what's the distance between me and the Earth, you would not say 0. If that was true, then if I were to dig a hole in the ground, I would not fall through it. I would just hover above that hole. But we all know that if I dig a hole right underneath my feet, I would fall down into that hole. Why? Because gravity is still at work. There's still a force of attraction that's pulling me down. And I would continue to pull down into the center of the Earth. And so that distance is always between the centers of their mass. So the distance between me and the Earth right now is not 0. It's so many miles, thousands of miles, because how far the center of the Earth is from me. And that's when gravity would cease to work. All right. So the square of the distance between them. So we see the formula we have here. We have proportional again, so we have a constant relationship. So that's our gravity constant. If you're in physics, there's a very specific value to this number. It's capital G, universal gravitation constant, times their masses, each mass of each object. That would give me this constant here. Divided by x squared. X is the distance between the objects and the square of the distance between them, which is why it's x squared. Inversely proportional, that's giving me the reciprocal. So inversely proportional to the square of the distance between them is the force of gravity, giving me another nice force function to use. And so both Hooke's law and gravity both give me nice examples of certain types of functions that have variable forces in which we can calculate work. And both of these force functions are functions we can deal with. We can evaluate antiderivatives, we can plug in some values and get answers. And so this kind of sets the stage for work, and in the next class we'll do some in the next discussion we will do some examples. So we'll work through some spring examples, some gravity examples, and one more. So the next video we'll look at applying this idea of work to calculating some work done for variable forces. So we will talk again soon.